All right, let's look at, we're going to look at Gaussian elimination, which is basically us taking a system of equations, converting it into a matrix, and using that matrix and then this elimination method to solve the system of equations. It's really slick. First, before we jump into actually solving systems, we need to figure out how to take a system of equations and write it as a matrix, okay? And we call it an augmented matrix. So the first things here is we're going to take, the top is just telling you how to do this, and I'm going to walk through the examples, and then you can read through the top 4 steps, okay? Basically, we have a matrix, a system of equations, and we can see that right now they're all lined up: x's terms, y terms, z terms, equal sign, constants. So when we convert this to a matrix, we actually are going to list all the coefficients and not list the variables. So here's what I mean. Coefficient of x's is going to be the first column, okay? Then the coefficient of the y, then the coefficient of the z, okay? And I'll talk about the constants in a second. So for the second equation, coefficient of x, coefficient of y, coefficient of z. Coefficient of x, y, z. Then we're going to indicate that there's the equal sign by using a vertical line. Okay, and then we're going to write the constants. So the top equation is equal to 3 and 6 and 4, like so. So we just took a system of equations, wrote it as an augmented matrix. Everything in this column are the coefficients of x. Everything in this one is the coefficients of y. Everything in this one's the coefficients of z. This is where the equal sign is, and these are the constants. Okay. All right, so just like we can take a system and write it as a matrix, we can reverse that and take a matrix and write it as a system, which is what we'll do next. Remember, these are the x's, these are the y's, these are the z's, equals, and then those are constants. And each row is an equation, okay? So it will be 1x minus 3y minus 5z equals -2. Next, 2x minus 5y minus 4z equals 5. And lastly, -3x plus 5y plus 4z equals 6. And there's the system of equations that's represented here. Okay. Now let's talk about Gaussian elimination method. All right. So because each row in these matrices represents an equation, we can do operations with the rows as if they were equations, because they are. Here's what I mean by that. Back when you were solving systems of equations, you did, we called it the elimination method, or some books call it the addition method, you know, where you take 2 equations, you line them up and you add them together. Okay, so what that's telling us is we could take 2 equations and add them together. So with matrices then, you can take 2 rows and add them together to create a row. Okay, now the only rule is that created row has to replace one of the ones you used to get it. Okay. Another thing that we did when we were solving systems of equations in the past is you could multiply an entire equation by any scalar you wanted. So any real number, I mean, you wouldn't pick 0, of course, but you could multiply by any number. You want to multiply the whole thing by 1/2, every single term all across the board, both sides of the equal sign. Okay. Now, you could combine the 2 of those things. You could multiply a row by anything you want and then add it to another row, creating another valid equation. Okay, so those are the operations that you can use when working with matrices, and that's what these are telling us below is the different operations that you can do. Okay, the reason, and it'll make more sense once we do an example, but I can interchange any rows, right? I can make any equation on the top or the bottom or the middle. It doesn't matter because they just represent equations. Okay, you can. I'll talk about these things again as we go because it'll make more sense. But you can add 2 rows together. You can multiply a row by a scalar or a combination of the 2. Okay. Now, for this Gaussian elimination method, our goal is to get a 1 in the very top left corner and zeros beneath it. And then diagonally a 1 in the 2, 2 spot, right? Row 2, column 2, and zeros beneath it. And then in the 3, 3 spot, a 1, zeros beneath it. And for as big as your matrix is, we would try to continue that pattern. Okay, so we're going to try to do that with this next example. Okay, so first goal, get a 1, 0 beneath it. Okay, now the reason that we want to do all of this and have a kind of a system for getting 1s and 0s is because if you had, I'm going to just let's go on the side. We'll go on the side here. Let's suppose for a second we had an equation that looked like this. 1, 6, 3 something. 0, 1, 0 something. 0, 0, 1, 5, 2, and then give me 30 seconds here. 15, 12. And let's suppose this was a 13, okay? Wouldn't it be really nice to say, hey, I just did all that work. Notice I got my ones and my zeros like we were supposed to do for this process. And the very bottom row represents an equation. This equation literally is z equals 5. It's practically solved. This one, y equals 2, that's slick. And the top one, 1x plus 6y plus 3z equals 13. That's solvable if you know the y and the z. So that's kind of big picture what we're doing here, okay? So let's go over to this example and do it. So first goal, get a 1 in the upper left corner, okay? And you can exchange any rows or you can multiply by a constant, okay? I am just going to write this as a matrix. 2, 3, 6, 1, -1, 1/2. Okay, and here's how I'm going to show my work. If I'm going to alter the row to the left, or excuse me, the matrix to the left, I'm going to use a lowercase. If it's going to become the next matrix, I'm going to use a capital. So here's what I mean. Row 1, my new row 1, and my new row 2 are going to flip-flop. So I'm going to write it like that to indicate that that's what I'm doing. So here's what this will look like then. 1, -1, 1/2, 2, 3, 6. Okay, so I flip-flop 2 rows. Now, I can interchange rows or I can multiply by a constant. I chose to interchange. I have a 1 in the upper left corner, which is my goal. Next is to get a 0 beneath it. Okay, we want to obtain zeros down that first column. So I want this to be a 0. Now, what can we do with equations? I can add them to other equations, or I can multiply by a constant. I'm not going to multiply by a 0, though. That wrecks my whole equation. Or a combination of the two, right? So in other words, here's what I'm going to say. My very next matrix, it's row 2, so it'll be my new one, is going to equal my old row 2, so I'm going to use lowercase, okay? And I can add and subtract equations. So my new row 2 minus 2 row 1, okay? Now, I'm not changing row 1. Okay, I don't have a row 1 here. I have a row 2 here. This is just my new row 2, not changing row 1. So row 1 is 1, -1, 1/2 still. Okay, using this formula, though, for each entry, I will have a 2 minus 2 times, what's the entry in row 1? A 1. That will give me a 0, and I'm going to put it in this new row 2 spot. Okay, but I have to do that for each entry. So for the next one, I'm going to say 3 minus 2 times a -1, which will end up being a 5. Okay, I'm going to go again. Next one, I will have a 6, because that's in the row 2 spot, minus 2 times what's in the row 1 spot, 1/2. So it'll be a 6 minus 1, I will get a 5 again. Okay, now I got my 1 in the upper left corner. I got my zeros beneath it. Now I'm going to go diagonally, and I need to get a 1 in the row 2, column 2 spot, which is here. Here's the trick. You don't want to introduce a number where you've already worked hard to get a 0. So don't add 2 equations together. Okay? At least not one from above it. So, because you want to keep the 0. So here's what I'm going to do instead. I'm going to take my row 2, and I'm going to multiply it by 1/5. Because if I do, my new row 2 is 1/5 of my current row 2. I'm not changing row 1. So I get that 1 where I want it. Or keep the 1 where I want it. Okay. The second row, however, 1/5 of 0 is 0, 1/5 of 5 is 1, 1/5 of 5 is 1. Okay. I have my 1 in the 2, 2 spot with any zeros beneath it. Well, my matrix is done, so I don't have zeros beneath it, but great. And then I would just keep that pattern until I have 1s along the entire diagonal, except for the constant column, right? And then zeros beneath them. Now, what am I going to do with this? We're going to take a look at what this means now. And we work kind of bottom up. Remember, this was the x column, this was the y column, and this is what the constant column. It's not what it equals, it's what the constant. So this very bottom equation literally is 1y equals 1. And then we're going to back substitute. Sorry about that. So what I mean by that is, if 1x minus 1y equals 1/2, and I know that y is a 1, I can add 1 on both sides now and solve and get 1.5, or 1.5 for x. So I used Gaussian elimination to solve for x and y. I now know that the solution to this system is x is 1/2 and y is 1. Or the solution as a coordinate point, right? These are both lines on a plane. So the solution is 1.5, 1. If I were to graph these, I would find that that's where they intersect. Okay? We're going to practice it again. Feel free to pause the video and try it on your own. Okay? All right, let's set up a matrix. Two, 1, 1, 4, 2, 6, like so. I need a 1 in this spot, okay? It's not very fun. I wish I could just add the two equations together to make a 1. I really can't, so I think what I'll do is just multiply row 1 by 1/2. So my new row 1 is 1/2 of previous row 1. Okay, 1, 1, 1/2, 1/2. Next row, I didn't touch row 2 at all. You know, I'm going to just say this right now. Sometimes I don't bother writing that vertical line, and it's okay. We know it's there. Okay, but now I need a 0 beneath it. So my new row 2 is going to be, I'm not going to multiply by 0 because that wrecks the whole equation. I'm going to say current row 2 minus 4 times the top row. Okay, I'm not changing the top row. Okay, what would this look like? It's going to look like 4 minus 4 times 1. The next one is going to look like 2 minus 4/2, right? Because it's doing 2 minus 4 times 1/2. Okay, so this will be a 0. That's interesting. Next one will be a 6 minus 4/2, which is going to be 6 minus 2, which is 3. Now, what does this mean? This is very interesting because I can't get a 1 here now. This means 0x and 0y equals 3. What's 0x and 0y is 0. A little frowny face. Is that even possible? Can 0 equals 3? No. Either I made a mistake or there's no solution to this system. Okay? Because this is a false statement. So false statements mean no solution. Okay? If you had, well, we'll have situations where there's true statements, and then what? Okay? So a false statement is no solution. Now, if we come over here to this, y equals negative 2x plus 1. It's going to be this line when you graph it. This one, let's see, 2y equals negative 4x plus 6, divide by 2. Oh, you know why there's no solution? Because these two lines are parallel. They have the same slope, okay? So there isn't any point in common. It's a no solution situation. All right. Feel free to pause and let's practice again. Three, 4, 12, 6, 8, 24. I need a 1. I can't add them together to get a 1, so I can't multiply by something to get a 1 either. So I'm going to say my new row 1 is 1/3 of current or previous row 1. 1 4/3-ish, 4, 6, 8, 24. Okay, and now I need a 0 right here. So my new row 2 is going to be old row 2 minus 6 times row 1, because I need a 0 and I can't multiply by 0. That would wreck the whole line. And I'm not changing the top equation at all. Or top row, yeah, top equation at all. So 1 4/3, 4. All right. Bottom is going to be a 6 minus 6 times 1. We got our 0. The next one is going to be 8 minus 6 times 4/3. Well, that's 8 minus 8. That's also a 0. Next one, 24 minus 6 times 4. Well, that's 24 minus 24. That's also 0. Well, what does this mean? This bottom row now, I can't diagonally get a 1. I already got a 0 and it's all across the board. This row means 0x and 0y equals 0. The previous example was a false statement. This is a true statement. So when we have a true statement, there's infinite solutions, and let's talk about what they are. There are infinite solutions, and, okay, there is a relationship with every x and y, okay? What do I mean by that? The solutions are the solution set of every x, y pair such that, now I can say x or y, one of them is any real number. Let's come to this equation. This is x plus 4/3 y equals 4. How about I solve for x? I would say x is equal to 4 minus 4/3 y. Okay, so here's what I'm going to say. As long as x is 4 minus 4/3 y, there's infinitely many solutions. So we're going to say that y can be any number. Here's my fancy any real number, okay? So y is any real number. And x can be, there's infinitely many, but it depends on what y is. So if y is a 0, x is a 4. If y is a 3, x is a 0, right? So there's lots of coordinate points that we will get out of this, but they have a relationship with each other. So it's not just willy-nilly any x and y. It's a specific x and y relationship. So there's infinitely many because this right here was a true statement. Okay, so you've seen examples now where there's infinite solutions, no solutions, and then a specific solution. Specific solution. Okay, and now we make our matrices bigger, but we still try to do this Gaussian elimination. Some books call it row echelon form, and actually Gauss elimination is getting row echelon form, which is the ones with the 0 beneath it, the diagonal one with the 0 beneath it, and so on and so forth. So for this example 6, when they want us to do row echelon form, we, instructors, we can call it Gaussian elimination. We can say row echelon form. Some people say REF, and I probably am one of those people, okay? So this is the 1, 0 beneath it, diagonally a 1, and then a 0 beneath it, and then diagonally a 1, 0 beneath it, and we continue the pattern. That's what we're going to do now, okay? Feel free to pause and try it on your own. Okay, I already have my 1 here, so step 1 is already done, but I need a 0 here. Okay, so my next line is going to be a new row 2. And I'm going to get it by doing current row 2 minus 2 times row 1. Not changing row 1. Not changing row 3. Just changing the middle one. So it's going to be 2 minus 2 times 1. The next will be negative 5 minus 2 times negative 3. So it'll be negative 5 minus a negative 6, so we'll end up with a positive 1. Next, 6 minus 2 times 4, we'll get negative 2. And lastly, 6 minus 2 times 3, which is 6, so we'll get a 0. And as long as you replace it in with one of the equations that you used, no harm done. So this is my new system. Okay, and now I need a 0 here. So my new row 3 is going to be my current row 3 plus 3 times row 1. I'm not changing row 1. I'm not changing row 2. I am changing row 3. So it'll be a negative 3 plus 3 times 1, 0. Next one will be a 3 plus a negative 9, because you're using this one and this one. The next one will be 4 plus 12. And lastly, 6 plus 9. Okay. So I have my 1s and the 0 beneath it. Next, diagonally, I want to get a 1, and I already have that. So I'm going to now work on what would come after that, which is to get a 0 beneath it, which is right here. All right, so my next line is going to be a change to row 3. So my new row 3 is going to be, I have to be careful. I'm going to use my old row 3, and I am going to say row 3 plus 3 times row 2. I don't want to use row 1 because I don't want a number in this spot where I've already worked really hard to get a 0. So I don't want to reintroduce a number in a 0 spot I've created already. Then I just go in circles. Okay. So what will this look like? Not changing the first row. Not changing the second row. I am changing the third. So it will be a 0 plus 0 for the first spot. Next, it'll be a negative 3 plus 3 times 1, because you're using this and this, for a 0. The next will be a 16 plus 3 times negative 2. It's a negative 6 for a 10. Next one is a 15 plus 3 times 0 is 0. Okay. I got my 1 with my zeros beneath it, diagonally a 1 with a 0 beneath it, and now diagonally with a 1 again. So I need to change that 10 to a 1. And I don't want to introduce a number to a spot I already got a 0. So my new row 3 is going to be 1/10 of my current row 3. This is legal math move because you're multiplying by a scalar, or a constant, or non-zero constant. All right, what is this? Top row is not changing. Middle row is not changing. Last row is changing. 1/10 of 0 is 0. 1/10 of 0 is 0. 1/10 of 10 is 1. 1/10 of 15 is 15 over 10. Both divisible by 5, so I could go 3 halves. Let's simplify it. Okay, Now I have my diagonal of 1s, my zeros beneath them. I'm content, and now I can start talking about what this means, okay? This one means, so these are x's, y's, z's. They didn't give us variables. It could have been a, b, c. We don't know. But I'm going to say z. So this variable z is equal to the constant 3/2. The next line means 1y minus 2z equals 0. And the top one means 1x minus 3y plus 4z equals 3. Now, here's the nice thing about these three equations. Top one, first one solved already, right? And if you know z, then this one, y minus 2, and z is 3/2. If y minus 3 is 0, then y is 3. So far I have x, I don't know. Y is 3, and I just automatically knew that z was 3/2. Okay? Let's use this bottom equation here. If x, right, top row if you want, right? If 1x minus 3y plus 4z equals 3, then I'm sorry, x minus 9 plus 4z, so 4 times 3/2 equals 3. I was looking here. All right, let's clean this up a little bit. This means x minus 9 plus 6 equals 3. X minus 3 equals 3. X is 6. So I have my x, I have my y, and I have my z, and I certainly could plug them into the system of equations, each equation, and make sure that they work, because that's how we check our answers. All right. Using your calculators. So here, it's practicing some by hand and then using a calculator. Here's what I'll tell you. I'm going to jump to number 8 and tell you that this means there's 0 x's, 1 y, minus 2z equals 0. 2, 3, there are no z's in this one, so there's a 0 there. -1, -2, 1, -1, like so. Okay, so don't be afraid to put zeros in where they belong. All right, I'm going to go up to this one. And I think you get the idea and the pattern, so I think I'm going to skip doing it by hand. But let's show you how to use your calculator to check your answers, okay? So let's suppose you do all the work for this one. The matrix that we're working with here is 1, -1, 1, 8. 2, 3, -1, -2, 3, -2, -9, 9. Okay, and the line was here. Okay, let's grab our calculators and then we're going to enter in that. Okay, get your matrix stored. Get your matrix stored. Remember, you go second matrix and then over to edit if you have this kind of calculator. And I entered my matrix in there. Okay. Once your matrix is in there, you can quit out of that and go back to matrix. And we are going to go over to the math option. And you're going to look in this list. And the craziest thing is I don't see RE. Do I see REF? I don't see an REF. Most calculators have just an REF, but I do see an RREF. So I'm going to go for that one because it's even better than REF. Okay. So it's RREF. I'll talk about what that means in a second. And then I'm going to insert, so second matrix, and I'm going to insert that matrix A that I already had. Okay. And I get this. RREF, not only does it do the first part, which is the 1, 0 beneath it, diagonal 1, 0 below, blah, 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 it also now puts zeros above it. So RREF is even better because we can see now that the very top equation is x equals 4, is y equals negative 3, and the last one is z equals 1. Let's see. Now, if you're a student of mine, a question like this would be on a no calculator portion of a test, because knowing that your calculator can take you straight to the answers doesn't show me any of your knowledge on how to manipulate them. A question like one of these, however, could show up on a calculator portion because it's not as much, it's testing, of course, can you solve the system, but it's also, can you set the system up? Okay, so a couple word problems here. Can you set the system? And if you use your technology at that point to solve it, so be it. Okay, Caroline invests a total of $12,000 into 2 bonds. One pays 10.5% and the other pays 12%. Okay, so I'm going to say bond A and bond B. Okay, so the total amount that went into A, I'll use the letter A, and the total amount that went into bond B is $12,000. That's one of the equations, just the money you invested. The next equation is going to be about the interest that they earned, okay? The first one earns 10.5% interest. Well, as a decimal, that is 0.105 times whatever the amount is in A. The interest earned on the money in account B is 0.12B, and this is $1,335 because it's just the interest, okay? Not total amount, it's just interest. So this one is on the amount invested. Second one is on the interest earned. I have 2 equations and 2 variables, and usually the rule of thumb is 2 equations with 2 variables, you can solve it. If I convert this to a matrix, I will have 1, 1, 12,000. The next one, I don't really like having decimals, so if I want to multiply this by 1,000, multiply this by 1,000, and multiply this by 1,000, it will be 105A. Whoops, I'm not wanting to put the variables in there, right? And 120B, and 1335, 1, 2, 3. I know those got big. It is what it is. Okay, this would be your matrix. Now, we set up the matrix. Can we solve the matrix? If you use your calculator and you do RREF, what will you get? Okay, you should plug it in and try it. Your answer should be, I'm just going to write it down so you can check it. Maybe. Oh, I don't know the answer off the top of my head. Turns out that you have 5,000 is the answer for account B, and 7,000 is in the account A. So $7,000 and $5,000. Now you check your answer and see if that's what you get. Okay. All right. This one will be, looks like there's 3 accounts. Okay, very similar process. I'll help you set it up and then you go from there. Total in 3 accounts. One is paying 5%, one is paying 8%, and a third one is paying 9%. The annual interest earned is $770. Okay. Oh, interesting. Okay, so we have whatever was put in A, whatever was put in B, whatever was put in C, equals $10,000. Okay. A got 5% interest. You know, I'll put them in as percents and then we'll change them. So 5% of that A amount plus 8% of the B amount plus 9% of the C amount got us a total of $770. Okay. Now I have 2 equations and 3 variables, so I need more. The last bit of information we're told is that the amount invested at the 9%, so that amount is C, was twice the amount at 5%. So basically, C is 2 times more than the A amount. Now, setup-wise, that last equation is not set up like we like. So I would not use that, but I would rewrite the equation so that it's a negative 2A, 0B plus C equals 0. Now it's set up like the others where you have your A's, your B's, your C's. Okay? As a matrix, this will look like 1, 1, 1, 10,000. The next one, if you want to do decimals, is going to be 0.05, 0.08, 0.09, and 770. I did not multiply by 100 across the board. I could. That's one of the allowed things. So if you want to change it to 5, 8, 9, then this needs to have 2 more zeros behind it. Okay? All right. And then the last one, negative 2, 0, 1, 0. Okay? That would be your system of equations. And you could grab your calculator and practice your RREF, and you should get A amount is $3,000. B amount is $1,000. And C would be $6,000 in the 3 different accounts.